Uh, so I hope you can hear me.
Yep, we can hear you and we can
Okay.
see your screen.
Okay, thank you. Thank you. Good morning, everyone. I hope everyone all doing good in this situation. I don't know what can I say. So I prefer to present face to face and meet you all, but unfortunately we couldn't. So I will present it via Zoom. Uh, I bring my name here only, and we have a lot of friends and colleagues, especially my professor, Dr. Desuki, in this research, but the names list are too long, so I prevent to put all name here. I combine both of presentation in one PowerPoint because of the time manner. Thank you for us to accept that, and also the title and the topic are so similar, so I combine both of them in one. So please feel free to stop me anytime you have a question, and I would answer any question in the presentation during the presentation. Okay, here I'm going to talk about the electromagnetic energy harvesting technology generally, and I will present two method and two uh, devices that we provided already. So let me start with a little bit introduction. Why we choose energy harvesting from roadway? So as we know, transportation is a sector that use a lot energy in comparison with other sectors in industries. So we said that, okay, why we don't use roadway infrastructure that are constantly subjected to different kind of energy and generate energy from transportation for transportation. So it's going to be green, renewable source of energy. So there are a different type of energy outside in the roadways, from solar radiation to heat to vibration, traffic-induced stress and deflection and other kind. In this study, we focus on electromagnetic mechanism to use the traffic-induced stresses and deflection to generate energy and convert it to electrical power. That the most useful kind of energy to power different devices in roadways. As I said, the goal gonna be develop novel energy harvesting solution application for lowest speed. In this case, we focus on lowest speed. Later on, you can see why we mean from lowest speed roadways. Uh, so the objectives were developing electromagnetic devices that they capture harvesting kinetic energy from traffic the displacement and then generate electricity. We performed a laboratory examination to see how it works, and also the feasibility are evaluated in this study. In this picture, you can see in this figure, you can see the way that tire interact with the pavement and also a speed bump and the force that it applied, that in some cases with the deflection or displacement is generate energy. So we use this energy with these forces to generate electricity. This is the final version of the devices that we supposed to present at the end of the research. We are almost close to this one, but here we just only present preliminary studies, not the whole mechanism, because it's under review and also under the test. In that case, you can see we use a speed bump. We said that, okay, why we don't use a speed bump? Because in a speed bump, we have a lot deflection and deformation that we can use even this deflection make displacement also to generate the highest value of the energy. Because of later on, you can see if we have a lot displacement, we will have more energy. It's gonna be like rack and pinion and other kind of technology, and also linear technology. I will explain them a little bit later. So here, before I go to reach the mechanism, I will present uh, the first part of the device that's gonna like subject it to force, top plate. We will, in this case, the yellow part. It's going to be exactly similar to a speed bump that driver feel it's a speed bump, that it will be a speed bump, but it move a little forward and upward and downward. So to allow us to have enough energy to generate electricity. We come up with different design for the top plate. We said that, okay, we can have it hollow or we can fill it with some material. We reach two group. In one group, it's the hollow group that gonna be include the metal, aluminum, and steel in this case. That because we want to prevent to make it very heavy, we make it hollow to see how it's gonna work. And then in the next group, we will have the frame from metal, again from steel and aluminum, but we put the heavy duty rubber on top of it, the material we already use in a speed bump, to see how they're gonna work. In this case, we studied them with abacus for finite element method. We use two different methods, static and dynamic. In a static model, we apply the two forces. Each one includes 3,773 Newton with the distance of 1.77 meter. We will find this value from the weight of the vehicles, and also the and the specification of the cars that we will have in our traffic. We go with the sedan car in this case, just for the model. It's going to be preliminary model, and we applied Young modulus for steel, aluminum, heavy duty rubber. As you can see, 200, about 70, and 3 gigapascal. And the Poisson ratio was 0.3 for, again, steel, and 33, and 0.4 for heavy duty rubber. In this page, you can see the result for the static model here. B was for aluminum, C was for steel, D heavy duty rubber, and E gonna be for heavy duty rubber with a steel frame. D is heavy duty rubber with the aluminum frame. As you can see, in the first group, we already have a lot of hysteresis also in the top of the plate, but in group B, we already have the frame that load subjected to load. The maximum stress can be seen in group A is kind of about 53 megapascal, but in group B, it was like 300 megapascal for the frame with the steel material, and about 100 megapascal for the aluminum frame and heavy duty rubber in top of them. It shows us how it works, and the maximum load was the contact between the top plate and the support that we have, and also the spring that we will apply under the top plate. And the result for deflection is presented in this table. As you can see, the best performances for steel is only 3.5. The deflection was measured in the middle of the bump because we have the maximum there. And as you can see, the best performances for steel, but others also have a good good shape. As you can see, the number was very low in comparison with the length of the top plate that is about 4 meter. That is so much. So the deflection is so low in that case, and all of them works in good shape. And also, as you can see from the result of stress, also the results are acceptable for all of them. According to material and kind of material, and we consider the drivers that will face this material, we come up with that result that maybe aluminum frame or a steel frame with heavy duty rubber gonna be the best option in this case. Any question? Okay, so it means that there is no question. Let me go to a dynamic model also. We also wanted to see and understand better concept of the passing load on the our top plate. So again, we applied the same loads as I mentioned before. The distance are the same because it's related to a specification of car, but the load pressure was 35 psi we use from the again car specification. In that case, it's Toyota Camry. And also I will explain a little bit more uh, about the device that we have, that you can see the spring, where the spring is applied, and the spring stiffness were about 7,000. And in this case, we go with the combination of heavy duty rubber and aluminum as a frame for that material. And you can, and also again, steel as a material. You can, hopefully I can present. You can see the wheel pass over the top plate. Top plate is going downward and then going upward, as you can see, yeah. Okay, so, and we have 4 different shot here. You can see the position of the wheel on the top plate and the stairs that is closed. It's not that much visible from here. Sorry for that, but you can see under the wheel that we have a different color that show the different value for the esters in this case. Here is another view from the passing car. You can see how the esters is generated in this case. The maximum is between the wheel and the support. Here you can see the result in this figure. The maximum when the wheel is over the top plate, you can see the maximum stress and how it's applied on the top plate. And let me show another wheel. You can see the stress on the support that we have and how it's visible. And in the figure, still you can see the maximum happen in the bottom of the support, in this case for the supports, and it's a little bit high in comparison with the top plate. So we have a spring under our top plate to move downward. After top plate go downward to recover it to the top again and make it ready for the next wheel passage. So we are done with the dynamic model for the top plate, and we reached that point that, okay, it's gonna be behavior the way that we like. So after that, we start generating the devices for the experimental study. And for the electromagnetic, we follow Maxwell-Faraday equation that mentioned that if we have difference in our electric field, we will have magnetic field, or vice versa. If we have a differentiation in our magnetic field, we will generate electric field. This is the first word preliminary for a linear generator. And let me explain. You can see the schematic also in the left side of the slide, and the sample in the right side, the device in the right side. Number one is the top plate, as you can see. Number two is the support for the tree. Number three, that is the magnet. And number two, supported and connect the magnetic to the top plate. And number four is the electrical coil that we will connect it later on to the device to measure the generated power. So what happened, as you can, let me to back here, as you can see, when we'll pass over it, top plates go downward and then move upward. So here, number one is to show the top plate is going downward and move the magnetic downward, and it's make a like differentiation in the magnetic field in close to the electrical coil, and then we generate electricity in electrical coil. And in the next device going to be a rotational mechanism. In this case, again, number one is a top plate, and four is the spring, two is the bottom plate. In that case, we can show it better. And three is the support. And again, number five is our two-part rod. How it works, two-part rod is one part is the stiff one, and that is going to be aluminum that allow us to move the other part of the rod, that is a rubber, that to push the lever down without generating any damage to the lever. And after that, the lever go downward and onward and convey the displacement to the package of the magnetic coils, gear, and torsional spring that we have inside our package number 7 here. We didn't open it in this figure. And again, this movement between the magnetic coil and gears generate electricity. You can see here. And then let me show you the experimental study in the laboratory. We also performed the field study, but I didn't bring it here in this presentation. So in experimental study, we connect our devices to the UTM machine, and then we connect it to resistance substitution box to have a resistance, and then connect it to NI DAC board that will record the output power, and then connect it to the system to record and analyze the output later on. And how we apply the load sinusoidally. As you can see, the load magnitude go up to reach A. I will explain a little bit later, and then go down and again go up. And we apply this continuous load again and again to see how our device work under the traffic load. After we assembled, we wanted to see what's the stiffness of our system and how it's gonna perform in this case. So we apply the force and measure the displacement point by point and go downward and then move it upward to see. And as you can see, it's really correlated to the result that the number, and the number is 140,000. That is really acceptable number for, in this case, especially in some part of it is because of the spring that we have in our sample for springs, and rest of them gonna be generated from our devices. We use Hooke's law to show the stiffness of our device under the load, traffic load. Here you are the shape of generated power under multiple loading cycle. As you can see in part A, it's going downward, part B is moving upward. This is for linear mechanism that we always generate power, because even we are going downward or even we are going upward, we have a different magnitude field that generate power in both cases. Sorry. As you can see, the output power, let me to make it a little bit. Oh, it's a little bit hard. As you can see, this is the result of the power. So we have different loading time and also different unloading time. We go with 300 milliseconds for loading and unloading, and increase it to about 1 second for each of them, because when car pass over it, they still have a speed, so we have very short time of loading unloading time. And also we have another in the left side. And we have also 3 different kind of load we are applied: 1 kilonewton, 2 kilonewton, and 4 kilonewton, as you can see. And the result is very low, but the thing is that the sample is the preliminary sample, and we are the beginning of this industry, so in this technology. So we need to be optimistic to believe that after we improve our and optimal our design, we will reach a higher point. Even though these values are good for some part of the small devices for traffic monitoring and other kind of devices in traffic and transportation infrastructure.
And Mohammed Reza, just to let you know, we have about 3 minutes left.
Oh, 3 minutes left. Okay, I will accelerate. Thank you.
Okay, thank you.
So, and here we have for the rotational, as you can see, we have only one peak for each loading unloading time. It's because our design is based on the way that we didn't generate any movement in our magnetic and or electric coil when it's moving upward. It's we need to improve that part with including new device, new part to our devices. And still, as you can see, the result is higher than the previous method, but it still is low. But we are also optimistic that we can increase the result after optimizing our devices. So here, the part that we can apply, we consider that you can see the unfortunately accident in a school zone in Texas and also San Antonio. There are so much, and we want to prevent, even though we can't do like things that we just save one person life, we did our job for life. So our suggestion is that we can input this device close to the school zone to generate power for at least light or a stop sign illumination. Also, we have cost analysis. If you can see the cost analysis for different energy harvesting method in roadways, electromagnetic is not the cheapest one, especially in comparison with conventional kind of energy fossil fuel, but still it's acceptable, especially in this stage of the development. And then we have the effect of our devices on sustainability. We will affect sustainability in transportation with increasing the safety and also generate clean energy sources. These were the maximum power output that we reach. You can see the maximum and also root mean square for both of the technology here, 140 milliwatt and 250 milliwatt for both of the devices. And we suggest how we can make improvement in our devices, make larger components for rotational, and also add more set magnet coil for linear generator. It's gonna boost our mechanism to generate more energy. And conclusion, as you can see, the results showed promising technology for harvesting energy from roadways. And also the electromagnetic with different mechanism can be considered a source of energy for future in smart roadways, especially. And the device will affect safety and sustainability in transportation without any doubt. So, and one of the good thing about these devices is that we can implement them in remote area that we don't have a power grid and generate power for devices and also other kind of light and everything in roadways. Thank you. I accelerate so to be on time. Thank you for your hearing. Thank you.
Thank you, Mohammed Reza. So we have 5 or 10 minutes to take questions, so we'll open it up now.
Nick, this is Samer. Would you mind let me share my screen just by the time we have questions, I can show you the field work that Mohammed Reza have done?
Yes, yeah, so I just invited you to be a co-host, so I think you should be able to share.
Okay, I will stop sharing. Thank you. You have my email here. Please contact me and ask your question. Thank you.
Stay on the line, please, Mohammed.
Okay, sure.
Okay, can you see the screen?
Yes, we can see it.
So here is the video. So the movements upwards and downwards, that's where it's going to be connected to our power generation devices, and it was actually collected here. And that's where the actual cutting that Mohammed have done in the field to insert his prototype. And it's looking like this when it is all finalized. Okay, and several cars he used in UTSA campus to test them in the to see how the functionality of those components will work, and you were able to pick up about 6 watts per pass, especially at a low speed. And the heavier the vehicle, the higher the load, the slower the speed, the higher the output power that he generated. Just want to have this since he was missing those from his presentation. I'm gonna stop my sharing now.
Okay, thank you very much. So yeah, if anybody has any questions?
Is any questions coming in writing? I don't see right.
Yeah, I'm looking. I don't see any coming in writing either. Any questions from anybody in the audience? If not, we can wait till the end, have a big Q&A session.
Okay.
Good morning. My name is Andreas Lanen. I'm with the New Mexico Department of Transportation. Can you give us a list of devices that your goal is to actually generate or energize with the system?
Sorry, I didn't get the question. Sorry for that. Could you please repeat?
What is your goal? What are the type of device that you can see being actually be energized utilizing the system?
The thing is that we are thinking about two ways. One is saving the energy and then generating power for existing devices. The other one is that we are connecting them like working concurrently. So in that case, our first goal is gonna be working on lighting, at least for a stop sign in this case, because we know that if we can light a stop sign, especially in remote area, we can like warn the drivers that we have a stop sign like in front of you, so lower your speed. Our first goal is that one, and then we can go with like new devices and transistors that we can apply for maybe a smart roadways that like observing collecting data and then sending for real-time monitoring of the traffic. In this case, we are just focusing on then, and after that we can, if we can improve it so much, then we can go for the higher value of energy. Then we can power different kind of devices in infrastructure.
Thank you.
Thank you.
This is Charles Rimke with the Department of Transportation. Can you hear me?
Yes, please.
The question that I have relates to consideration to maintenance activities and potential impact of movement associated with sand and dirt infiltration. Have you guys given consideration on how that could be mitigated?
About the maintenance part, you mean?
About the functionality and the operability from over time having sand and dirt infiltrate into the actual mechanism.
Yes, it's really, thank you for a great question. So yes, we consider that part. Unfortunately, I couldn't bring it here. So what we're gonna do, we seal it in two way. First way, we're gonna use our aluminum box around the whole device to prevent to go anything inside. Still one more protection gonna be again with the aluminum and also with the very small part of the rubber to seal completely our device part, like electromagnetic generating part, because spring still we have some problem with the spring, but we will seal all components in the way that we don't need to maintain it like in a very short time. But definitely we need to maintain it for long time, but the maintenance gonna be like similar or even longer than the pavement maintenance, definitely. And if something happened and we need to maintain our devices, the good thing about is that we can remove it from the body of the pavement and put a plate or something instead, or even though the top plate there, and then maintain it outside and then return it inside the pavement. And the thing is that in the worst case scenario, if the top plate can move downward or upward, it's gonna behave exactly like a speed bump, the conventional speed bump, and we don't have any problem with the traffic flow in that case. Did I answer the question? Thank you.
Yeah, I think we have time for one more question here. If anybody has one more question, or else I think we should have some time at the end to ask some more Q&A. All right, well, that sounds like it's about it. So thank you very much, Mohammad Reza. That was a very interesting presentation. So up next, I will...
Thank you, Nick. Thank you, everyone. Have a good one.
Oh, and I guess, Mohammad Reza, did you say that you needed to run? So will you be here for Q&A if we have any at the end, or?
Unfortunately, I'm at work and I just figured that I need to present today. So because of that, I didn't have time, but you can feel free to contact me via email, and I will be more than happy to answer all questions that we have.
Okay,
thank you.
Sounds good. Well, thank you very much.
I will be on the line if you have any questions, follow-up questions by the end.
Thank you.